Okay, so this video is going to be about section 9.2 in the book. It's all about chord properties. Just as a reminder, a chord of a circle is any line segment that connects 2 points on the circle to each other. So that would be a chord. Before we move on, you had the answers in the homework yesterday. I'm just going to scroll through those real quick. This one at the end, I did want to talk about very quickly. So the idea here was you've got this geostationary satellite, and it's kind of sitting above the Earth. If this is 30 degrees, remember we've got 90, 90, which means we can subtract from 360 because this is a kite. It's got four sides. So 360 minus 90 minus 90 minus 30 makes 150. And then so that's this angle. This angle is 150, which also means that this arc measures 150. And either way we want to think about it, if we're talking about what percentage is visible from the satellite, we can view 150 degrees of the whole thing. And the whole Earth is 360 degrees. And that gives us 41.67% of the Earth that's viewable. So that's what's going on with that one. Now, when we're talking about chords here, there's going to be a lot of properties. I think there might even be like 6 of these. But in all reality, it's kind of 2 properties that they're wording from several different directions. So at the end, I'm going to summarize kind of the 2 big things you're going to want to take away from this one. So first off, just a quick little reminder on some vocabulary. A central angle. A central angle is any angle where the vertex is at the center of the angle. So this red one, this black one, or that green one, all central angles. None of these angles in here are central angles. And so a central angle has its vertex at the center. Compare that to an inscribed angle. An inscribed angle has, all 3 points of the angle are on the circle, or it has the vertex on the circle and it crosses through the circle 2 other places. And so there's your definition. An inscribed angle has its vertex on the circle and its sides are chords. In other words, meaning that as you go out along the side of the angle, it's going to hit the circle again on either side. None of these are inscribed angles. Here the vertex is outside, here the vertex is at the center. Here this side hits the circle again, but this side never does. So that's why those are not inscribed angles. We're going to talk about those much later on, or a lot more later on. So here we go. Let's talk about some of these properties. So our first one is called the chord central angle conjecture. And it says if 2 chords are in a circle are congruent, they determine 2 central angles that are blank. And so the question is, what do you think would be true about those 2 angles? We've got a little exploration here we can pop open. And you can see here, I've got it so that these chords are the same. I can move them around. It does seem to want to break on me. Come on, you're not going to let me drag it around? It does want to break on me there. I'm not sure what I did wrong on that one. But if I show the central angles, you're going to see until it breaks, they always stay the same. And that should make sense. What's going on here, if we want to argue deductively about this, is we've got 2 chords that are the same. All of these are radii, so they're the same, which means these 2 triangles are congruent by SSS. And so these 2 angles are congruent as well. So if 2 chords in a circle are congruent, they determine 2 central angles that are congruent. And so the big thing here is that those 2 angles there and there are congruent because those 2 chords are congruent. The second one here is literally just the exact opposite of this one. If 2 chords in a circle are congruent, then their blank are congruent. And so now we're talking about these chords being congruent. And so we already knew the central angles were congruent. Sorry, not the exact opposite, like one extra step. And since those central angles are congruent, that means the arcs are congruent too. So their arcs, its technical word would be intercepted arcs. Arcs are congruent. So this arc and this arc is congruent. And if we accept that that last one is true, then this one is obviously true because the measure of this arc is just equal to the measure of these angles. The angles are congruent. The arcs have to be congruent as well. So those 2 conjectures, they're listed as 2 separate conjectures, but they're really the same thing. If the angles are congruent, the chords and the arcs are. If the chords are congruent, the angles and the arcs are. All the same thing because those triangles are congruent. Okay, this one's a slightly different idea. It says the perpendicular from the center of the circle to a chord is the blank of the chord. And so they're looking for a fancy math word here, but again, I've got a little exploration of this. So I've got a circle with a chord in it. I'm going to go ahead and construct the perpendicular radius, or perpendicular goes to the center, and then show the measure of those two chord pieces. And I'm going to move this around. And as long as I stay on that side of the circle so it doesn't mess up my construction, you'll see those are always equal. And so the definition here, or what's going on here that they want us to get to, is that if I have a chord and I make a perpendicular through the center, it's got to be through the center, the perpendicular line is the bisector, is the fancy word. It cuts it in half. Of that chord. So when you see some example questions at the end here, you're gonna see some algebra or some missing pieces that you have to find. Okay, this one. Two congruent chords in a circle are blank from the center of the circle. So if I take a circle, got another exploration here. If I take a circle and I make two chords that are congruent, we measure distances perpendicularly. So what would you think about those two lines I just drew in? Well, you'll notice if I make the chords closer to the circle, those lines both get smaller. No matter what I do, I change one chord, the other has to change to stay congruent, and you'll notice that those measurements are always the same. And so as you get closer to the center of the circle, the chords get longer. As you get further away from the center, the chords get shorter. But as long as they're the same distance from the center, the chords are the same length. So two congruent chords in a circle are equidistant, is the word they're looking for here. So equidistant. Remember, that just means the same distance. So as long as you've got a circle with two chords that you know are congruent, if that one's congruent to that one, then that distance and that distance have to be the same. Okay, one more here. The perpendicular bisector of a chord. So if I were to take this chord here and draw in the perpendicular bisector, meaning it's perpendicular and it bisects the chord, it is going to go through the center of the circle. So that is just the exact opposite of this one here. So this one said if it's a perpendicular from the center, it cuts it in half. This one said if it's perpendicular and cuts it in half, it goes through the center. So those are just the exact opposite. So what that means is we've essentially got two main conjectures here. We've got the conjecture that has to do with the perpendicular to a chord. So if I draw on a chord and make it perpendicular, it goes through the center, perpendicular, and bisects. Those three always happen together. If you have two of those things, either perpendicular, bisect, and through the center, any two of those things will automatically make the third one true. The second one has to do with our chords and arcs. So if I have, in this picture here, if these angles are congruent, so are these chords, and so are these arcs. So again, if any one of those is congruent, the other two are as well. The other thing that kind of goes along the same idea as this is if those two chords are congruent, the distance to the center is the same. And again, that's just because those two triangles would have to be congruent. So those two kind of fall in the same thing. There were two conjectures here that were really all the same. There are actually three conjectures here that were really all the same thing, kind of worded in three different ways. So let's go ahead and take a look at just a couple of examples here. But remember, you can always go back and look at these. So congruent chords are equidistant from the center. Can we say anything about distance from the center if one chord is longer than the other? Yes, we talked about that. The longer chord is further from the center. Nope, that's backwards. I showed you the picture and it made more sense. Longer chord is closer to the center. All right, if I have to draw a chord way out here, it's going to be pretty short. If I draw the chord in here, it's going to be really long. The diameter that actually goes through the center, that's the longest chord. And then the second one here, what is needed to ensure that two arcs have the same size and shape? They could have the same central angle. And then you'd also have to have the same radius. If they were in the same circle, you wouldn't need the same radius. But if they're in two different circles, they would need to be the same size circle and the same central angle. Okay, so let's take a look. This is what some of your questions are going to look like. So we've got AB is 14. This is supposed to be arc AB is 110 degrees. So I'm going to put 110 out here. We want to find what's the measure of angle CAD and what is the measure of angle B or DB. So let's go with this one. If I know that this is 14, I can see that line DC is perpendicular and goes through the center. So I know right away, well, it also has to be a bisector. Right? That's this first one we talked about. If it's perpendicular and it goes through the center, it's also a bisector. So if AB is 14, then I know that DB is 7. So they got 7 and 7. Okay. Next up, I know that AB, the arc, is 110 degrees. Well, that tells me that this angle in here, change colors, that angle in there is 110. And since I know this is an isosceles triangle, we've got two radii there. And it's a triangle, 180 degrees minus 110 gives me 70. And I've got two angles left over that I know are congruent because it is an isosceles triangle. So we've got 35 degrees on each one of those. Next up here, we got a little bit of algebra. So we got a circle that says AB is congruent to CD. So these chords are the same length. What that tells us is that they are the same distance from the center of the circle. So I know that 2x plus 6 has to equal 24. And that's an equation I can solve. So I'm just going to subtract 6. 2x equals 18. And I can divide by 2, and x equals 9. So I'm just using that property that chords that are the same length are the same distance from the center of the circle. So that's what you're going to see in a lot of these here. You're doing 1 through 9 and 11, so you're just skipping over 10. Tomorrow we can definitely take some time and go over these before we talk about section 9.3. And then we're going to be taking a break on Wednesday and doing just a review over these two because the chords and the next one's going to be about those central angles and inscribed angles. They have a lot of conjectures going on. Most of them really do make sense when you look at them, but it's a lot to remember. Like when you first see a picture, what's true here? So try those questions out. Make sure you're looking back at those conjectures that you have and not forgetting, things like in this picture here, I can add these all up and I know that they have to equal 360, that kind of thing. So you got the rest of the class, work on these, and I'll see you tomorrow.